There we go. Hello there. I am Jeffrey Wade, and this is problem number 7 of the CPSC5210, the design and analysis of computer algorithms. And this is the knapsack problem. Problem number 7 is the knapsack problem. And we will continue. Problem number 7. The objective of problem number 7 in the final exam was to illustrate the application of dynamic programming on the knapsack problem. The knapsack has a maximum weight of 7 pounds. There were 2 constraints, I should say, on the problem. Okay, the knapsack has a maximum weight of 7 pounds, and the second constraint is the electrical chargers should be paired with their related device, e.g., a cell phone should be with its cell phone charger, or a laptop should be with its laptop charger. Here is the item table of all the items in question, and their monetary value, as well as their actual physical force on the earth due to gravity. In American units. Weight, pounds. Cell phone weighed 1 pound. The charger weighed 1 pound. The laptop weighed 3 pounds. The charger for the laptop weighed 1 pound. The tent weighed 4 pounds. The medicine weighed 1 pound. The instant food weighed 2 pounds. The water bottle weighed 1 pound. The umbrella weighed 1 pound. And the flashlight weighed 1 pound. Now, in the problem, okay, the total weight of all items was 16 pounds, okay, and it was figured that the most expensive item per weight, or per, I should say, the most expensive item, dollar divided by pound, or dollar per pound, would be the medicine per unit pound. Okay, it was the most expensive per unit pound. The modeling of the data, optimizing the solution. The question at hand, there was not an implication of a pecuniary interest of profit or savings. Okay, the wording of the question was purely worded in regards to the force on the knapsack itself, meaning that there was the maximum weight. What would be the considerations of the maximum weight? Now, there was no speak of intrinsic value as far as what a practical consumer would do either within the knapsack problem. So it was kind of not exactly arbitrary. Is that the word I'm looking for? It was very easy to go different directions with the problem, the way the data could be modeled. There was many different viewpoints upon optimizing for a solution. I guess that's what I should say. Food for thought. There could be, I thought of personally, 3 types of optimizations depending on the entity of interest. Okay, so entity number 1, say you had like a bargain shopper, and Walmart was running one of their deals, as far as anything you can put in a knapsack that weighs less than 7 pounds in the whole store you can have, up to 7 pounds. We're running this for a minute and a half at midnight. It's a blue sticker sale. Okay, they do stuff. They have similar type offers like that on occasion, but there's usually nothing's usually given away for free. But and then another potential optimization would be for the practical purposes individual, okay, who is shopping for the purpose of having the item itself. For instance, to go on a hiking trip, and someone who likes the outdoors, something like that. All right, and then the third type that I thought of, which I probably thought of many other ones. Okay, but a third type would be the retailer. All right, an entity who would be trying to run some type of sale and a combination sale to move more volume. So figuring out the highest price, say anything you can fit into a bag, anything you can fit into a bag that weighs less than 7 pounds will knock 30% off. Our profit margin is 50%, and we're going to run this through the weekend because our volume is slow and our projected figures are to make in profit, even though we're making, by knocking 30% off, we would only be making 20% profit margin after marking up 100%. But we would sell projected 3 times as many goods this way. That would be another type of situations or instance where that could be. Those numbers. It is very hard to find any item that is 100% markup. Okay, and if you do, you better quit your job, invest in it, and keep doing it, because that's very hard to find. Anyways, continuing on. To all the viewers out there, not that I'm an expert in business, but I do know that 100% is very good. It's a very good profit margin. So that's doubling the price for what you paid for it in order to sell it. All right. Considering the 4 concepts, characterize the structure of an optimal solution or desired solution. Okay. Recursively define the value of an optimal solution. Compute the value of an optimal solution, typically in a bottom-up fashion. Construct an optimal solution from the computed information. All right. Multiple solutions. Depending on the entity in question, what is the optimization goal? Well, we've already stated that, right? So, for the purpose of this presentation, to give solidify the concept and to solve the problem, we will use the bargain shopper. Okay, the items in a knapsack giveaway at Walmart for the Blue Lights Special. That is what particularly this presentation is going to be. If I was a shopper, how could I optimize my sack to get the most value in items into my sack? How would I potentially do it if they were to have this giveaway? All right. On the flip side of that, a retailer could indeed try to say, how can we maximize our profit by allowing customers to put only 7 pounds into the bag, by giving them a discount upon whatever is in the bag that weighs 7 pounds or less to increase volume. Okay. Now keep in mind that this model did not take into the account of it only takes into the account of the force weight in 2 dimensions. It does not take into the account the three-dimensional effect that's going in the knapsack as well. For instance, a tent in the knapsack sounded a little crazy to me, but to some practical person, that might have been the way to go. If they were an outdoors lover or something. All right. But here's how the ranking system went for the bargain shop for the blue light special. For the knapsack giveaway, anything under the bag that weighs up to 7 pounds, you can have it in the whole store. A ranking system. Each item has two weighted categories: price and weight. Okay. Sort the rankings of both categories. Add recursively sort, of course. Add each member's ranking position in each category. So whatever the weighted rank within the population of a member in the category of price, for instance, if a member had a weight of being the 6th best, okay, plus being 2nd, you would take the 2. Of course, six best is really, really bad. So you would take the 2 and add them together. And then whatever that comes to, no, wait a minute. You would take you take each member's position ranking. The better you did, so if there was 5 out of the population, if there was 5 members and you came in first place, you wouldn't be the number 1 person. You'd be you'd be ranked at the top of the 5. You'd be the king of the king of the tree, so to speak. All right, you'd be on top of the tree. So you would get 5 weighted points. Okay, and that is how the ranking system would work. So if your item was the highest priced item and it was the lowest weighted item, say for instance something like diamonds, yeah, say you had like a couple carats of diamonds, that would be ranked very high in both price, and ranked the inverse rank of weight would be very high as well. Okay. Or the inverse, yeah, that's right. So sort the rankings of both categories, add each member's ranking position in each category, and then divide by 2. So whatever the average is of the individual rank in the population of each category would be the average of the 2. The items with the items with the highest overall combined average would be the first to go into the sack up until 7 pounds or less. All right, for the special cases, okay, items paired together. For instance, the device was paired with its charger. They must go together. Items will be factored in as one item. So the total of their price going into the ranking and the total of their combined weight going into each ranking, and they will count as one unit. All right, because they must go together. So instead of having 10 individual items, since those two must go together, either they're in or they're out, there will only be 8 individual items. instead of 10. Okay, the cell phone and the cell phone charger, the laptop and the laptop charger will, those are 4 items. They will count as 2 items. All right. That's the one process. That's part of the constraint. So that's what we will do. Continuing on. The algorithm. Mapped rank weights. So the items and the weights. For all items, recursively sort the weights. If then one item ties for rankings, each member gets the average of the population of ranks for n1 through n size equals rankings, and returns items in the weight. For instance, if their half the population is tied for one, then tied for first place, then the average of first, second, third, fourth, which would be half the population in this case, of adding the positional numbers of 8, 7, 6, and 5. When you add those together and divide by 4, it would weight across, and that's what you would get in that particular category. Repeat the map for price. Mapped rank price, items price column. For all items, sort price column. If more than one item ties for rankings, each member gets the average of the population of ranks for n1 in size rankings. Okay, so that would be the average out of the group's portion of the population's rankings. All right, the rankings are going to be determined altogether. There are 8 potential contestants in each category. Every contestant has a positional rank based on how well they do. The best ranking would be 8. 8, 7, 6, 5, 4, 3, 2, 1. We would add those up. The summation of all the possible rankings would be 21, 26, 30, 36. Okay, so 36 is the total population. If there were 3 people who tied for the first of it, then that would be considered their position times whatever portion of the rank there is. Continuing on. Overall average of ranks. Ranking within weights. The lowest weight is ranked higher in this situation than the highest weight because of the fact that the more weight, the lowest weight, would fall within the constraint and would overall weight be a stronger component with its weighted price, of course, going into the SAC. All right, plus the key price ranking. All right, so the weight of rank plus the price of rank, meaning that the ranks of the two, or it might be better put, the rank of weight plus the rank of price, divided by 2 is the overall ranking. Okay, so just like this would be very similar to a modeling contest. The more models they're always worried about their weight. So the one with the lowest weight, she would be like all happy because she's like the best model or whatever. Yeah. Anyways, in conclusion, for the bargain shopper, it was found What is the greatest bargain in knapsack giveaway? Okay, it was found that the items of the combination medicine, laptop, charger, cell phone, and charger were the greatest bargain in the knapsack giveaway as far as price per unit pounds. Okay, so for the bargain shopper gets the best deal by grabbing the medicine, the laptop charger, the cell phone, and the cell phone charger, and putting them in the knapsack in the given time. All right, that's how they're going to get the most value out of their 7 pounds. With that said, guys, without saying anything else, I hope you have a very good evening, very good day, very good morning, whenever you see this. And this video is stopped.